Welcome to this deep dive into a fascinating piece of research you shared with us. I have covered all the bases here, interpreting reasoning features in large language models via sparse autoencoders. For those just tuning in or looking for the TLDR, this paper kind of cracks open the black box of LLM reasoning. Using sparse autoencoders on DeepSeek R1, the researchers identified specific internal reasoning features, essentially neural pathways linked to logical thought.
Yeah.
The really cool part, by tweaking these features, they could directly influence the model's reasoning abilities, boosting or hindering its performance on complex tasks. It's a foundational step towards truly understanding and controlling how these models think. Okay, let's unpack this.
That's right. It's one thing to see these large language models perform, sophisticated reasoning, but this paper gives us a much-needed peek under the hood. The authors tackle a really fundamental question for anyone working with LLMs. How do these models move beyond just pattern recognition to actual reasoning?
Exactly. We've seen this incredible evolution, haven't we? From just predicting the next token to engaging in multi-step problem solving and even showing what looks like, self-reflection. The paper rightly points out the impact of techniques like chain of thought prompting.
Right. Okay.
Which encouraged models to kind of articulate their reasoning, and self-consistency decoding, where, generating multiple reasoning paths improves the final answer.
And now we have specialized architectures like OpenAI's O1 and DeepSeek R1, the focus here, that are really pushing the boundaries through advanced training methods. What's particularly exciting about this paper is that it directly grapples with the internal mechanisms behind this progress. How are these reasoning capabilities actually encoded within these vast neural networks?
It's the question many of us in the field are asking. We see the impressive results, but what's the underlying machinery? The paper touches on this idea that within the complex web of a language model, meaningful concepts might be represented as specific directions in its activation space. Can you elaborate on what that implies for someone visualizing the model's inner workings?
Sure. Think of the model's internal state as this massive, multi-dimensional landscape. Each point in this landscape represents a specific activation pattern. The hypothesis is that certain directions you can sort of move within this landscape correspond to activating specific concepts.
Okay.
So moving in one direction might strongly activate the concept of cause and effect, while another direction might relate to mathematical equality. The challenge, of course, is finding these meaningful directions in this incredibly high-dimensional space.
Which leads us to the central technique in this research: sparse autoencoders, or SAEs. Now, autoencoders themselves aren't new, but the sparse aspect seems crucial here for interpretability. What makes SAEs particularly well-suited for this kind of investigation into LLM reasoning?
You're right. Standard methods for trying to understand these dense activation patterns can become, very difficult to interpret. SAEs offer a more structured approach. The fundamental idea is to take these complex internal activations and decompose them into a relatively small set of underlying features. The sparse constraint forces the model to represent each activation using only a few of these features, ideally leading to a more disentangled and interpretable representation.
So sparse means that for any given input, only a select few of these learned features will be significantly active, rather than like a diffuse activation across many features.
Exactly. It's like having a set of highly specific detectors. Instead of many general-purpose detectors firing weakly, you have specialized detectors that fire strongly only when their specific concept is present in the input. This makes it much easier to understand what each individual feature might be capturing.
Okay. So how do these SAEs actually learn these sparse feature representations from the LLM's activations? What's the training process look like?
The process involves taking activation vectors from an intermediate layer of the pre-trained LLM, in this case DeepSeek R1, and training a separate two-layer autoencoder on these activations. The encoder part of the SAE maps the high-dimensional LLM activation into a lower-dimensional but sparse feature vector.
Right.
The decoder then tries to reconstruct the original LLM activation from this sparse vector.
So the SAE is essentially learning a compressed sparse code that can accurately represent the original denser activations within the LLM.
Precisely. The training of the SAE aims to minimize the difference between the original LLM activation and the reconstructed activation. That's the reconstruction loss. Simultaneously, a sparsity-promoting term is added to the loss function. The paper uses an L1 penalty on the activations of the hidden layer of the SAE.
Ah, the L1 penalty.
This L1 penalty encourages most of the feature activations to be 0 or very close to it, enforcing sparsity. Equation 2 in the paper formalizes this total loss as the sum of the reconstruction loss and a weighted L1 penalty.
And equation 1 lays out the basic mathematical structure of this two-layer autoencoder. We see how an input activation X is encoded into the sparse feature vector F through a weight matrix and a nonlinearity like ReLU, and then decoded back to X hat using another weight matrix. As the paper highlights, the columns of that decoder weight matrix, DDESC, are crucial because they represent the learned features themselves, the directions in the original activation space that the SAE has identified as important.
Exactly. Each column of Lebedeck can be visualized as a vector in the LLM's original activation space.
Ooh.
When a corresponding feature in the sparse code F is active, it means the original LLM activation had a significant projection along that specific direction, indicating the presence of the concept that feature has learned to represent.
Okay, so the researchers now have this tool, the SAE, that can give them these sparse features. The next crucial step is figuring out which of these features are actually involved in reasoning. This is where the reason score metric comes into play. What's the core idea behind reason score?
Well, the core idea stems from the hypothesis that features specifically involved in reasoning should be more active when the model is processing language associated with reasoning. Think about human reasoning. We often use specific types of words and phrases when we're thinking things through, expressing uncertainty, or exploring different options.
Right.
The researchers called these reasoning words.
And they observed in the original DeepSeek R1 paper that the model itself sometimes spontaneously generates these kinds of introspective linguistic patterns during its reasoning process, almost like verbalizing its thoughts.
Exactly. So to make this more rigorous, they wanted a way to quantify this. They created what they called a reasoning space by analyzing the OpenThoughts 114K dataset, which contains both math problem solutions and the reasoning steps generated by DeepSeek R1 to arrive at those solutions.
Okay.
They compared the frequency of words appearing in the reasoning traces versus just the final answers.
That's a clever approach, looking for linguistic patterns that are characteristic of the reasoning process itself, not just the outcome.
Precisely. But they went further to isolate words truly indicative of reasoning. They filtered out high-frequency words that appear commonly in general language using the Google Books Enneagram corpus. Figure 2 in the paper beautifully illustrates the top 30 words that show the greatest increase in frequency in the reasoning traces after this filtering. You see words like, but wait, let's, so, and maybe prominently featured.
Those definitely sound like words you'd expect to see during a train of thought, yeah. From this analysis, they compiled a reasoning vocabulary, denoted as R.
Yes, a carefully selected set of words they believed were strong indicators of reasoning. Then they developed the reason score metric, formally defined in equation 7, to assess how much each individual SAE feature contributes to reasoning based on its activation patterns.
Let's break down reason score. It seems to fundamentally compare how much a given SAE feature activates when the model is processing tokens within this reasoning vocabulary R versus when it's processing any other token. Is that right?
That's the essence of it. The term psi in equation 4 calculates this difference in the average activation of a feature on reasoning tokens versus non-reasoning tokens, normalized by the overall activation of that feature. So a higher psi suggests the feature is more responsive to reasoning-related language.
But they also incorporated an entropy penalty, as shown in equations 5 and 6. Why was it important to consider the entropy of a feature's activations across the reasoning vocabulary?
The entropy penalty serves to favor features that activate more consistently across the entire reasoning vocabulary. You don't want a feature that only lights up for a single word like maybe, but is silent for all other reasoning indicators, right?
Right.
The entropy term high quantifies how uniformly a feature activates across the different words in R. A higher entropy indicates a more uniform activation, which is desirable.
And then reason score in equation 7 combines that initial score psi with this entropy term high raised to the power of alpha. So alpha acts as a hyperparameter controlling the balance between a feature being specifically responsive to reasoning words and being broadly applicable across them.
Exactly. In their experiments, they set alpha to 0.7. After calculating the reason score for all the thousands of SAE features they learned, they focused on the top 100 highest scoring features for detailed manual inspection.
What did this manual evaluation process entail? How did they actually determine if these top scoring features were indeed related to reasoning in a meaningful way?
Well, they built an interface that allowed them to examine numerous instances where each of these top features activated. They could see the specific text context, the tokens that caused the strongest activation, and crucially, how the activation of the feature influenced the model's output probabilities, the logits for the next predicted tokens.
Okay.
They were looking for features that consistently activated in contexts indicative of reasoning, such as logical deductions, expressions of uncertainty, causal reasoning, and exploration of alternatives. They also checked if activating a feature pushed the model to output words associated with reasoning, and if the feature's activation pattern held across different types of reasoning tasks. Through this rigorous process, they narrowed down a set of 30 features that they believed were most strongly associated with reasoning-related properties.
That sounds like a very involved but crucial step to ensure the validity of their automatic scoring method. Now, to really establish a causal link between these identified features and actual reasoning behavior, they moved on to empirical analysis, including what they called feature steering. Let's start with the individual feature examples they highlighted. Feature 17456 was one of them. What did they discover about its role?
Feature 17456 proved to be quite insightful. As illustrated in Figure 3A of the paper, it significantly increased the model's preference, so higher logits for words associated with reflection, like research and consult.
Interesting.
Furthermore, as shown in Figure 3B, this feature consistently activated in textual contexts where the model appeared to be engaged in logical or evidential reasoning. This suggests a strong link between the specific internal feature and the model's capacity for reflective thought processes.
Another interesting example was feature 15136, detailed in Figure 4. What key aspects of reasoning seem to be associated with this feature?
Feature 15136 exhibited an interesting influence on both negative and positive output logits, hinting at its role in helping the model differentiate between possibilities. Examining the text examples that maximally activated this feature, presented in Figure 4B, revealed its involvement in seeking clarification, considering alternative approaches to a problem, and generally double-checking its work.
Ah, the double-checking.
Yeah, it seems to be connected to the model's ability to refine and validate its reasoning steps.
And then there was feature 46379, as shown in Figure 6. What kind of reasoning-related behavior was linked to this one?
Feature 46379 appeared to influence the output probabilities of words like actually and actual, which are often used when reporting a finding or making a correction. The activation examples in Figure 6P showed it being triggered in contexts where the model was checking information, explicitly looking something up, or considering different methods, again pointing towards a role in ensuring the accuracy and correctness of the reasoning process.
Finally, they discussed feature 62777, depicted in Figure 7. This one seems particularly relevant to the idea of self-correction, which is, a hallmark of sophisticated reasoning.
Indeed. Feature 62777 strongly impacted the logits associated with words like opposite, reverse, and inverse, suggesting an understanding of negation and alternative perspectives. Its activation in contexts containing phrases like wait, no, and explicit corrections, as you can see in Figure 7b, strongly indicates its involvement in the model's ability to identify and rectify errors within its own reasoning process.
So these individual feature analyses provide qualitative evidence supporting the idea that the reason score is indeed picking out components related to reasoning. But the paper takes it a step further with feature steering. Can you explain what this technique entails and why it's important for establishing causality?
Right. Feature steering is a powerful technique to directly investigate the causal effect of these learned features on the model's behavior. The basic idea, as formalized in Equation 8, is to take the model's internal activation at a specific layer and add a scaled version of the decoder weight vector corresponding to a particular SAE feature.
Okay.
By adjusting the scaling factor, lambda, you can effectively amplify or suppress the activation of that specific feature during the process of generating text.
So they're not just observing correlations, they're actively manipulating these internal representations and seeing how it changes the model's output, allowing them to test if a feature truly causes a change in reasoning behavior. The paper mentions they focused on reasoning-related attributes like strengthening causal links, improving deductive inference, and encouraging structured argumentation.
Exactly. They systematically varied the strength of the steering, the value of lambda, and then analyzed the resulting text both through manual inspection and using GPT-4o to help with more automated evaluations of reasoning-related properties. Table 2 in the paper summarizes some of the reasoning clusters they identified using GPT-4o, essentially grouping features based on their apparent function when steered.
Okay.
You can see clusters related to reasoning depth and thoroughness, numerical accuracy and validation, self-correction, and even the balance between generating code and providing explanations.
Table 3 then provides a more granular view of how steering those specific example features we just discussed, 15136, 17456, 46379, 62777, actually impacted the model's reasoning behavior. It's striking to see how amplifying feature 15136, for instance, consistently led to more detailed and iterative reasoning with instances of self-correction.
Yes, the examples presented in tables 4 through 8, which show the model's output on a variety of problems, both with and without feature steering, really illustrate the power of this technique. You can observe how amplifying these reasoning-related features often results in longer reasoning chains, more explicit self-correction steps, and ultimately improved accuracy on challenging problems. For example, in the how many R's problem in Table 4, the steered version exhibits a much more detailed and self-reflective thought process before arriving at the correct solution.
It's almost like giving the model a focused boost in its reasoning capabilities by directly manipulating these identified internal components. To further validate these findings, they also conducted steering experiments on several established reasoning benchmark datasets, like AIM 2024, Math 500, and GPQA Diamond. What were the key outcomes on these benchmarks?
As detailed in Table 1, they consistently observed an increase in the average number of output tokens produced by the model before it gave its final answer when reasoning features were amplified through steering. This suggests that steering these features encourages a more extensive internal thought process. More importantly, they also found statistically significant improvements in the accuracy of the model on these challenging benchmarks when specific reasoning features were steered, providing strong quantitative evidence for a direct link between these internal representations and enhanced performance on complex reasoning tasks.
This is quite compelling evidence. It really seems like they've successfully identified and can causally influence specific internal components that are fundamental to the reasoning abilities of these advanced language models.
Absolutely. The combination of the reason score methodology for identifying promising features, the detailed empirical analysis to understand their function, and the causal interventions through feature steering provides a robust and multifaceted argument for their conclusions.
So, to bring it all together, this deep dive into the paper, I have covered all the bases here, reveals a truly groundbreaking approach to dissecting the internal mechanisms of reasoning in LLMs. The innovative use of sparse autoencoders and the introduction of the reason score metric offer a tangible way to pinpoint and even manipulate the specific features that drive these complex cognitive processes within models like DeepSeek R1. The causal evidence derived from the feature steering experiments strongly reinforces the idea that specific interpretable components within LLM representations are indeed directly linked to reasoning behaviors.
And for you, as someone deeply engaged in the technical aspects of AI research, this work offers a fascinating and I think crucial insight into the how behind the impressive reasoning capabilities we're increasingly seeing in these models. It moves us beyond simply observing the output and starts to reveal the underlying machinery that makes it possible.
And the implications of being able to identify and influence these reasoning features are potentially huge for future research. I mean, imagine the possibilities of being able to fine-tune a model's reasoning strengths for specific tasks by directly manipulating these internal components. It could pave the way for more controllable, explainable, and ultimately even more powerful AI systems.
Definitely. And it opens up a wealth of further research questions, How do these reasoning features emerge during the training process? Are they consistent across different model architectures and scales? Can we leverage this understanding to diagnose and address specific types of reasoning failures in LLMs?
Yeah, lots to think about. The researchers encourage a deeper look into the paper, particularly the appendices, which contain further details on the identified features. We encourage you to do the same. What are your initial thoughts on this mechanistic account of reasoning in LLMs? What further avenues of research does this work spark for you? We'd love to hear your perspective as we continue to explore the fascinating deep structures of AI reasoning.